Good afternoon.
You're muted, Dharma.
Yes, I just realized. Sorry. Okay, welcome everybody to our webinar series titled Celebrating Women in Space for the World Space Week. I think if people don't mind, I'd like to give people 1 more minute to join us and then we'll begin the seminar. Okay, we can get started. Good afternoon again, everybody. My name is Katamzi Joseph. I'll be your host for today's session. We are in a webinar series for the World Space Week. Our webinar is, the speaker for today is Dr. Lee-Anne McKinnell. She will be presenting on space solutions from Hermanus. Dr. McKinnell is currently the Managing Director responsible for the Space Science Directorate located in the Hermanus facility of the South African National Space Agency. She has held this position for 11 years, prior to which she was a researcher with a joint appointment with Rhodes University, as well as previously the Hermanus Magnetic Observatory. Dr. McKinnell received her PhD in space physics from Rhodes University in 2003, and her PhD work was on the development of the neural network-based ionospheric model for the bottom side electron density profile over Grahamstown, South Africa. After her PhD, she completed a postdoctoral year as a research fellow at the Graz University of Technology in Austria. Her research areas of specialization are ionospheric physics and space weather. In 2015, Dr. McKinnell received her MBA from the Business School, Netherlands. Welcome, Dr. McKinnell, and we look forward to your presentation.
Thank you very much.
Before we continue, I'd like to bring to everyone's attention that we have a competition going on. At the end of the webinar, Dr. McKinnell is going to pose a question, and the correct answer is going to win something from SANSA. I can't remember exactly what it is. Also, if you've got questions, can you please put them on the chat box, and at the end of the of Dr. McKinnell's presentation, I will then ask her all your questions. Thank you.
All right, thank you very much, Dr. Katamzi Joseph, and welcome to our participants and welcome to World Space Week. It gives me great pleasure to present to you today on space solutions from Hermanus. I'm going to share my screen now. One moment. for a moment. Sorry, Herman, I'm having trouble here.
Is it turning the display off? Because we could see it when you had it on.
Can you see the actual slideshow?
Yes, we see the slideshow, yes.
Okay, all right. It's just showing that it's showing another window here. Okay. My apologies for the technical difficulty. We will proceed now. So today, it gives me great pleasure to talk to you at the beginning of World Space Week and to launch this webinar series, Women in Space from Hermanus today. The title of the presentation is Space Solutions from Hermanus, and I'm actually going to take you on a journey through the past 80 years of how we have developed an Hermanus facility into a place which provides unique products and services to South Africa. So the outline of the talk today, I will start with where it all started, do a little bit of magnetic observatory history, talk about where are we now, so the path from magnetism to space science, where are we going, so shaping the future. I'll touch on space weather, and then some exciting developments here in Hermanus, and then conclude. So where did it all start? So most people ask me the question, why Hermanus in the Western Cape, apart from the fact that it's a beautiful place to be, what brought us here and how did we start here? So the facility in Hermanus started off as a magnetic observatory, and the facility here in Hermanus was created in Cape Town, and it came through an era of exploration. So if we want to really go back to where it all started, we need to go back to 1841, to the Cape of Good Hope, which was known as the era of exploration. During this era of exploration, between 1600 and 1700, visiting sailors from Europe have been responsible for the early magnetic observations in South Africa. So actually, magnetic observations in South Africa have gone back a long time. In fact, in 1538, the Portuguese navigator de Castro measured magnetic declination at the Cape 6 degrees east of true north, and used that for navigation purposes. In 1595, Cornelius Houtman, commander of a Dutch fleet, on its way to India, obtained a value of 0 degrees at Mossel Bay on land. And then we skip all the way to 1818. Freycinet was responsible for the first complete determination of the magnetic field at Cape Town, and that is where it really all began. In 1841, the Cape of Good Hope Observatory was established on the grounds of the Royal Astronomical Observatory, and a Royal Artillery detachment was responsible for the observations. And these observations continued until 1853, when the observatory was unfortunately destroyed by fire. But as you can see, very early on in our history, magnetic observations were a very important part of the path that we were coming. And helped a lot with navigation purposes, particularly around the Cape of Good Hope. So here are some of the early observations, and we're very proud we still have records going back to 1840 of that period of time where we took declination measurements. And of course, these measurements were taken by hand, so it was quite an accomplishment to have those records now. And this graph shows how the declination changed between 1840 and 1903. So if we look at the timeline of early history of magnetic observations that I've just shared with you from 1538 to 1903, some of the important milestones that dictated and sort of set the scene for our movement coming forward was the 1535 measurements, measures of De Castro, who measured the magnetic declination of the Cape Coast. The Dutch commander, who obtained that declination value of 0 degrees on land at Mossel Bay. Then 1600 was also a very defining moment in our history, because an English physicist, William Gilbert, stated that the Earth is a giant magnet. And a lot of our physics and our understanding of magnetism and how it impacts on us on Earth started with the declaration that the Earth is like a giant magnet. And those of you who have done physics at school will remember that when you see a picture of the Earth with the Earth's magnetic field lines coming in and out, it looks like a giant dipole with the magnetic field lines coming together at the poles. And that came from that understanding. And then if we look at the period between 1841 and 1853, the Cape of Good Hope Observatory was established at the Royal Astronomical Observatory and operated by a Royal Artillery Detachment led by Lieutenant Frederick Erdley Wilmot. In 1903, it was also a defining moment as the first comprehensive geomagnetic field survey of Southern Africa was compiled. And this geomagnetic survey is something that we still do today, except obviously using more modern methods. So we then skip to the Magnetic Observatory history, the Magnetic Observatory being the SANSA facility in Hermanus at the moment. And we skip to the International Polar Year and to the University of Cape Town in 1932. The Polar Year of 1932 to 1933 prompted the establishment of a Magnetic Observatory at the University of Cape Town. The Magnetic Observatory was established in 1932 under the leadership of Professor Alexander Ogg. And this was the first time the Magnetic Observatory had been re-established since the fire in the late 1800s that had destroyed the Cape of Good Hope Observatory. And this observatory at UCT continued to take measurements of the Earth's magnetic field until the 1940s, and the subsequent electrification of the suburban railway network became a disturbing influence. So when you're going to take measurements of the Earth's magnetic field, you want a magnetically clean or quiet environment. It limits the number of disturbances you're going to get on your measurements. So you want what we call an absolutely quiet, from a magnetic point of view, environment. In the 1930s, the South African Railway Company was growing, and they had started to electrify some of the railway lines. And this electrification had a disturbing influence on the observations that were being taken by the Magnetic Observatory. When you have an electric railway line, the electrification of the railway line induces its own magnetic field, and that magnetic field is quite significant, can therefore cause disruptions in your measurements. So a new magnetically clean site had to be identified, and the site in Hermanus, where we are today, was identified. The site was moved here in 1941, and the Hermanus Magnetic Observatory officially commenced operation on January the 1st, 1941. So this year, we are celebrating 80 years of magnetic observations out of the Hermanus site. This is just a little bit of the history. I've already mentioned why Hermanus was chosen. It was a magnetically clean site, and the Magnetic Observatory was relocated here in 1940 and started operations on the 1st of January 1941. At that point, the Magnetic Observatory belonged to the Department of Lands, but in 1969, it was incorporated into the Council for Scientific and Industrial Research. Essentially, the Magnetic Observatory worked quite well under the CSR until the late 1980s, when the CSR started to commercialize some of its services, and it tried to commercialize the Hermanus Magnetic Observatory at the time. This was unsuccessful, and in the late 1990s, the CSR made the decision to close down the Magnetic Observatory. However, there was an international outcry due to the contribution that the Magnetic Observatory was making to the global magnetic field measurements, and eventually the HMO was declared a national facility and transferred to the National Research Foundation. The SANSA Hermanus facility remained as a Hermanus Magnetic Observatory for 10 years under the NRF, and in 2011 was migrated to the newly established South African National Space Agency, where we are today. This is a picture on the top left of what the facility looked like in 1941. There was just a few buildings on the site. The land that the site was positioned on is in the West Cliff suburb of Hermanus. We have 16 hectares of land here, and the buildings were built sort of roughly around the middle of the land available. This is a picture of the front facade of the building today. So this is our reception area where we come in, and the property has been quite extensively developed as we've grown in terms of our capability over the years. More on that later. A little bit of a look at the history of the instruments involved. So the instrument on the left-hand side here is a local photographic magnetometer, and the instrument on the right-hand side here is a Schuster-Smith declometer. And these are instruments that were used to measure the Earth's magnetic field at the time, so 80 years ago. The instrument on the right-hand side we still have today, although it's very hard for us to find experts who know how to operate that instrument today, because today's magnetometers are much easier to operate and more and less manual. The photographic magnetometer required a paper change, so somebody had to come in every so many hours and change the paper, because the magnetogram, which gave us the magnetic field measurements, was actually printed on photographic paper at the time. Looking at the Magnetic Observatory over the years, I've already mentioned Alexander Ogg. Alexander Ogg was the managing director of the Magnetic Observatory from 1932 to 1946, and he was instrumental in moving the Magnetic Observatory from Cape Town to Hermanus in 1940-41. Mr. Van Wyk, A.M. Van Wyk, took over in 1946, and he remained managing director until 1977. In this photograph, we have the last 4 managing directors, including myself. So in 1977, Dion Kung took over and was managing director till 2000, and Peter Sutcliffe took over from him in 2001 and led the observatory till 2007. Zandila Malinga led from 2007 to 2009, and I took over from him in 2010. So we have the last 6 managing directors on the screen in front of you. And what is interesting is that each one of the managing directors had a particular role and interest in the Magnetic Observatory in ensuring its sustainability, whether it was moving it from UCT to Hermanus, whether it was moving it from the Department of Lands to the CSR, or from the CSR to the NRF, or from the NRF to SANSA. Each move created a leapfrog in the history of the observatory. Now we move on from 1932, so till 2011. So in 1932, the Magnetic Observatory was established. In 1941, the Magnetic Observatory was re-established in Hermanus and commenced operations here in Hermanus. In 1960, the Magnetic Observatory also joined the South African Antarctic Expedition, SANAR-1, and in 1969, the Magnetic Observatory was then incorporated into the CSR. In 1987, some of the services provided here, particularly in our magnetic technology group, were commercialized. In 2001, the Magnetic Observatory was declared a national facility and transferred to the National Research Foundation, and in 2011 was transferred again, this time to the South African National Space Agency. The 2001 transfer of the Magnetic Observatory was a transfer for survival, and the 2011 transfer was a strategic transfer. And by that, I mean that the Magnetic Observatory was escaping being closed down, but when it was moved to the NRF, it was also given the mandate to grow the business of magnetic observatories, of observations, to be a space science contributor to the country, and to ensure that this facility remains a national asset. And the transfer in 2011 as a strategic move into the space agency proved that that had been accomplished in the 10 years preceding, because now the facility was set up to become a space science facility for the country. So where are we now? I've spoken about magnetism and how we've moved from all the 1800s to the 1930s, from 1932 to 2011, and looking at how we grew from a magnetic observatory to a space science facility. So on the 1st of April 2011, I mentioned already that the HMO was declared a national facility and migrated from the CSR to the National Research Foundation. At that point, we had approximately 9 employees remaining on site, and some of the activities had already been commercialized, like, for example, the magnetic technology. Moving on 10 years, the HMO was declassified as a national facility and migrated from the NRF to the newly established SANSA as a custodian of the space science program for South Africa. At that point, there were 36 employees working in the facilities, and the activities were mixed. So some commercial, some public good, and some pure research. The migration was strictly a strategic move. So looking at where we are now, so now we're 10 years into SANSA. So I should mention this as well, that we've celebrated 80 years of magnetic observations in Hermanus. We've celebrated the move from CSR to NRF, from NRF to SANSA, and now 10 years on the 1st of April 2021, we celebrated 10 years in SANSA. At that point, in terms of people, we have 66 employees on site, 25 students are supported through our program. Our infrastructure, including the buildings that were here 10 years ago, now includes a techno lab, a science center, which is now 15 years old, a research building, student residence and guest house, and garages. Our instrumentation, and this is the interesting part of how we've become unique and able to provide national infrastructure for space science research, is the growth in our instrumentation. So we have approximately 90 individual ground-based space instruments. These are, by the way, located at approximately 20 unique sites around Southern Africa, Antarctica, and the islands. We're an active member of the South African National Antarctic Program, and currently 80% of the South African shore-based equipment at the South African base is owned by SANSA and is used for space weather studies. We have the only large 3-axis Helmholtz coil system in Africa, located here at the Hermanus facility, and we also have 4 intermagnet accredited geomagnetic observatories, which means that we operate fully 24/7 4 observatories that provide magnetic observations to the world at a particular standard, that is international standard that is set. So what is SANSA Hermanus and what do we do these days? So we're still a magnetic clean facility, but utilized now for a broad range of space science related activities. So the original reason for moving to Hermanus is still valid and is still something that we strive to protect in terms of this facility. We are still a part of a worldwide network of magnetic observatories, and we contribute continuously to the global magnetic observation network. We're responsible for research infrastructure and data, which is used to monitor the near Earth space environment. Another way of putting this is that we're really good at measuring space from the ground. And then we also do fundamental and applied space science research, postgraduate student training, science advancement, and we provide space weather and magnetic technology products and services to various industries around the country. Some interesting facts about the work that we do here at SANSA Hermanus. So firstly, the first campus we calibrated was a Watts Datum campus in 1964, which used to be on a Shackleton aircraft. And now one of the things I want to mention, one of the unique services that you can provide from a magnetic clean environment, which we've been doing since the 1960s, is the calibration of landing compasses. And we've calibrated many, many compasses over the years, roughly about 200 a year. And the first compass was a Watts Datum compass in 1964. The Magnetic Observatory has been providing geomagnetic field modeling data to the defense industry for more than 25 years. And that data is used for mapping purposes, so inclination and declination information. Initially, the magnetometers were all photographic paper-based and very manual, and someone had to change the paper and feed the magnetometer once per day. So 365, 24/7, somebody had to come in and feed the magnetometer. The electronic technology was only introduced in the 1970s, and then still for a number of years after that had to be watched. I mentioned that SANSA Hermanus is located on 16 hectares of land in Hermanus. This land is owned by SANSA for the sole purpose of executing SANSA's mandate. The Absolute House, which is the place where we take the absolute measurements of the Earth's magnetic field, is still located centrally on the property, and the magnetically clean area is still preserved today and is still part of our uniqueness in terms of what we can offer. SANSA researchers have produced 168 peer-reviewed high-impact journal publications in the last 6 years, with 71 of them first authored by a SANSA research student. And this is a very good statistic because prior to 2004, 2003, 2004, research was a very small part of what was done from the Magnetic Observatory, and we've increased that considerably. So over the past 6 years, we've managed to really increase our research output, giving us the credibility we need. And I'm going to talk a bit later about the importance of credibility as well as a sound database. Here's just some photographs of our equipment. So on the right-hand side, we have the absolute house, which I mentioned is the place where we take measurements of the Earth's magnetic field. We have a declination, inclination, declinometer in the middle, and we have a Helmholtz coil system on the left-hand side. The Helmholtz coil system is the only one in Africa and is used for taking out the Earth's magnetic field when you want to get the absolute characteristic of a dynamic platform that contains a magnetic signature. So this is where we've come from and where we are now, and now where are we going? So shaping the future, looking forward. So SANSA has a 5-year plan that includes this facility and the work that we do here. And the 5-year plan includes the development of products and services for the space and non-space sector, but from our knowledge, expertise, and credibility in the space arena. It's about developing, second priority is about developing key infrastructure that we can utilize for service in the country with products and services. It's about knowledge. So SANSA's plan is to assist the country in moving from a resource-based economy to a knowledge-based economy. So developing knowledge, research into the near-Earth space environment, making sure that we develop sound products and services built on sound research. Human capital development is our 4th strategic priority. So that is looking at developing the skills we need for the space agency of the future, but also looking at how do we inspire to aspire learners and the youth in terms of STEM subjects, science, technology, education, mathematics, etc. And then our 5th priority is to be a key enabler of government's priorities. So to ensure that space works for the country and our knowledge and our space-based knowledge and know-how is useful for that. So how do we do this? So some important considerations are, what can we take to the bank? So some advantages from a facility like this one. Firstly, data is our currency. So we have a very large database going back many years, and that data is our currency. It allows us to do all the work that we do, from research to applied to products and services development. Our infrastructure is unique and specialized. It would be extremely costly to set up what we have here again, taking our 80 years of expertise into account, plus the infrastructure that we've built up over time. Much of it is infrastructure that you can't find anywhere else and can be used for unique products and services. Our geographic advantage is also one of the things we can take to the bank. So the fact that we're in Hermanus, so a magnetic clean environment, that we're in South Africa, that we're in Africa. So we are considered to be a gateway to Africa by many space scientists in the world. And then also our positioning on the Southern Hemisphere, being experts in measuring space from the ground. It is very good to be in a country that is located in an area that is largely unpopulated by space science instrumentation. Then we also look at what is trending. So what are the opportunities? Now, one of the opportunities, which I'm going to talk about next, is space weather. And space weather is a global challenge with regional impacts. So the African space industry is growing, and with that growth comes the dependence on items such as space weather and how we address that. And we've been positioning ourselves to be the African partner in terms of addressing space weather as a global challenge. Then the 4th industrial revolution and future dependence on technology will also require space expertise to protect that technology. And then there are international regulations regarding space weather information. So in doing this, the SANSA has put together a project called Operationalize Space Weather, which is a 3-year project that is now 2/3 of the way into it. The project is around providing 24/7 operational space weather services to the African region by November 2022. This came about due to a designation that SANSA received to provide space weather information to the aviation sector on behalf of the International Civil Aviation Organization. And this was a designation that was given to SANSA based on the fact that one of the unique capabilities we have in Hermanus is a space weather center. So by operationalizing space weather, we were able to develop capability, derive economic benefit, provide a national platform, ensure credibility, fill the expertise gap, provide quality services, contribute to the knowledge economy, create opportunities and partnerships, and increase the value proposition for space science in our country. And so that is one of the reasons we have put this forward as our plan for the future. And now, because by now you're all wondering what is space weather and how does that fit into this, I want to introduce you to the topic of space weather. And to do that, I have a very short video to share. I'm just a little bit unsure about the sound, so we're just going to check whether the sound will work. Please let me know, Herman.
Why is it important? What is the threat? What is the impact on technology? How does it differ from terrestrial weather? What is space weather? The Earth, our home, orbits our life-giving star called the Sun. The Sun is not only extremely hot, with a surface temperature of about 6,000 degrees Celsius, but it also has certain activities happening on its surface, like solar flares, coronal mass ejections, storms, and heat, basically emitting millions of particles, radiation, and energy into space. This causes space weather. And even though the Sun is about 150 million kilometers away from Earth, our planet can still be affected by space weather. Just like Earth's weather has seasons, space weather has seasons too. The Sun has a cycle of about 11 years, known as solar minimum with low solar activity and solar maximum with high solar activity. But even during times of low solar activity, solar storms and solar flares may occur. Solar flares are giant explosions on the surface of the Sun that occur when twisted magnetic field lines suddenly snap and release massive amounts of electromagnetic energy. A solar flare takes about 8 minutes to reach Earth and travels at the speed of light. Charged particles from solar storms can reach the Earth in a mere 20 minutes, while coronal mass ejections, which is a large cloud of charged particles, will take 1 to 4 days to reach the Earth. When the magnetic field of a coronal mass ejection interacts with the Earth's magnetic field, it causes a temporary disturbance known as a geomagnetic storm. Space weather is constantly interacting with our Earth's magnetic field, but the impact of a space weather storm will not harm humans and other life forms on Earth, as we are protected by the Earth's magnetic field. The Earth is a giant magnet, and the field it generates acts like a shield against solar particles and radiation. However, our astronauts, the aviation sector, and satellites are at risk if satellites are hit by space weather. Radio communications, telecommunications, navigation and weather services may be affected, and many more electronics can suffer hardware errors and failures. This can disturb internet connectivity, have an effect on your cell phone, interrupt satellite TV, and even cause radio blackouts. In severe cases, the power grid may be damaged. Astronauts also have to be aware of space weather and should avoid spacewalks during space weather events in order to avoid the radiation from the Sun. Passengers and crew on long-haul flights can also be exposed to radiation during space weather events, which is why the International Civil Aviation Organization recommends that space weather information be included into flight plans. But the effects of space weather interacting with our magnetic field can also be spectacular. The magical lights in the sky, called aurora, are an effect of space weather storms such as solar wind, solar energetic particles, and coronal mass ejections. And while we enjoy the beautiful views from our balconies, looking up into the sky, we can remember that our magnetic field is working non-stop to keep our planet safe. Scientists from around the world are constantly monitoring the sun and our magnetic field to predict space weather and warn of their effects. The South African National Space Agency is expanding to do this on a 24/7 basis and offers several products and services to mitigate the effects that space weather may have.
Right, so I hope that the sound came through there and you were able to see this short video, because it's a very quick way for me to demonstrate the importance of space weather and why we study it. So as you would have seen in the video, we mentioned the aviation sector, and I mentioned that SANSA has received a designation as a regional center for space weather information provision from the International Civil Aviation Organization. This designation was received after an audit process that proved that SANSA has the capability and capacity to move towards providing a 24/7 space weather service to the aviation sector. We are very proud of the fact that SANSA was one of only 5 designated centers globally. We were designated as a regional center for Africa, and there were 3 global centers, the US, a consortium from Europe, a consortium, an East-West consortium, and then the other regional center designated was the China-Russia consortium. So we were very proud of this, but this also gave us the catalyst to move into the future, to start operationalizing space weather, to start looking at space weather not only as a research field, but also as an operations, something that we could use to provide products and services to help mitigate the impacts of space weather. In particular, the aviation sector interested in 4 different domains: high-frequency communications, satellite communications, GNSS-based navigation and surveillance, and radiation exposure at flight levels. And the SANSA Hermanus facility has already become a center of excellence for high-frequency radio communications, as our focus over the past 10 years in providing space weather information has been around HF communications. The agreement we came to with ICAO was that the regional centers would be ready to serve the aviation sector from November 2022, and that the global centers from 2019. We are now, we put together a project. This is just a brief summary of the project, and we looked at what we needed to do to take us from where we were in 2019 to where we need to be in 2022 in order to operationalize space weather, but also develop the credibility and the support and the foundation for providing a good operational service. So our project is now 2/3 of the way through. It's divided into 7 parallel sub-projects, including the construction of a brand new 788 square meter space weather center, which I'm going to show you a picture of in a moment, including ISO certification for quality products, products and services development. So we need to increase our numbers of products and services. Also, communications, business development, and marketing is very important. If you're going to offer a service, you need to market that service. Skills, capacity, and capability development. So we needed to look at ensuring that we had the capability and capacity by 2022 in place to do this. ICT architecture and systems development. So looking at the backbone of ICT architecture that the facility would be built on. And then also the African Instrumentation Network, which is the expansion of our geophysical network to include more ground-based instruments throughout Africa to allow us to get more data, real-time data from Africa in order to be able to provide a better service. All of these projects are running in parallel, and they will conclude in an operational space weather capability by November 2022. So if you look at the calendar, you will see that we have exactly more or less 1 year left to do this in. Okay, so now we have this beautiful, unique facility that has an 80-year history, and we've been building on it to establish capability that provides, makes us a national asset for the country. And part of that is the expansion of our current buildings on site. So this is a look at the timeline for the building project. So we are currently sitting around here, where we're busy with phase 1A to 1C. And the phases include the building of a new space weather center, which is 788 square meters, as I mentioned. It will have a 24/7 operations center, which will be a little bit like a mission control room. It will have an auditorium, a 100-seater auditorium. So hopefully webinars like this in the future can be given in person as well. And it will have office space and boardrooms for the space weather team. We also building a new generator house in support of the space weather center, as reliable power is a prerequisite for being able to provide the service. We're also building some new accommodation, guest house and student accommodation on site as well, as we anticipate that the number of people using the center will increase dramatically as well. So this is a picture of our site for those of you who have been here. This is the site as it was on the 19th of April, our building site where we're building the space weather center. This is the picture taken of the building construction project last week on Thursday. And you can see that they're at roof height already. So we are anticipating that our December deadline will be met. What are we aiming for? This is the architectural impression of what the space weather center will look like. This will be the auditorium on the right-hand side here. The control center will be in the middle, and then we will have some boardrooms and offices at the back here. These are just architectural pictures of the other auxiliary buildings that are in support of the main building. This center will be a state-of-the-art space weather center, the only one on the African continent, providing operational services 24/7, and it will be located here within the magnetic environment of SANSA Hermanus. And the reason we can do this is because we have this 80-year history. We also have incredible data sets that allow us to provide unique information. And we have knowledge, know-how from the space environment to back it up. And we have a very capable and well-equipped set of researchers who provide us with the research and the know-how around the near space environment. So in conclusion, some concluding points we want to make here is that I mentioned the Hermanus facility. So this facility has a rich history of more than 80 years of magnetic observations. This is a facility that South Africa can be proud of and that will continue to deliver for South Africa for many years to come. The facility and the space science program that it is the custodian of have grown considerably over the past 20 years, ensuring that we provide credible space solutions for the space and non-space sector. We are not done yet though, and 2021, 2022 and beyond promises to be exciting for SANSA, the Space Science Program and Hermanus. We will build on the foundation of data, environment, expertise and infrastructure to ensure a sustainable future for this remarkable facility with an enhanced value proposition. And you may think that I'm a little bit biased because I'm very involved in this facility in terms of my outlook on it. So I invite you to visit us for one of our public tours. We are commencing public tours again this week. If you're not from Hermanus and you don't have a prospect to visit anytime soon, there is a Hermanus virtual tour of the facility on our YouTube channel, which I also invite you to go and have a look at and take yourself on a tour around this remarkable facility that has come a very long way in the last 80 years. Thank you very much for listening, and I really hope that you enjoy our World Space Week webinar series. Now, I believe that I need to provide you with a question so that you can participate in the competition. And so I'm just going to pull up the question. Is that right, Zama? You want me to provide the question?
Yeah, you can do that, Lee-Anne.
Okay. So the question for today's webinar is, on what date did the Magnetic Observatory officially commence operations in Hermanus? I will repeat, on what date did the Magnetic Observatory officially commence operations in Hermanus? Please do not put your answers in the chat. You have to collect the answers from all 5 questions. Zama will tell you exactly what to do in a minute and email them to an address that Zama is going to give you. Thank you very much for listening today.
Thank you, Lee-Anne, for that interesting presentation, information on not only the history of Magnetic Observatory in South Africa, but also space science and what we are aiming to do in the future. As Lee-Anne has said, if you could just please hold your responses or your answers to the questions, because we have a series of the webinars. There are 5, so 1 each day throughout the week, and each webinar will have questions. At the end of the week, if you then have all the answers, you could then email them at I think at info@sansa.org.za. I'll also put the email address on the chat there. So thank you, Kiera. I see you've already posted your answer. So you give everyone a freebie for this, for today's question. But yes, if you can just answer all 5 questions. So regarding the 4 upcoming webinars, then you email them at spacescience-info@sansa.org.za. So without any further delay, I'll get into questions now. But as Lee-Anne is responding to questions posed, if you have any more, please just put them on the chat box. So the first question comes from Douglas Moyeni. He has 3 questions. The first question is about, do the power cables also affect the magnetic observations? Because you said earlier how the Magnetic Observatory was moved from Cape Town because of the electrification of the train lines. So Douglas would like to know if the power cables have the same effect on the magnetic data or measurements.
Do you want me to answer them one by one?
Yes, let me just ask, otherwise you might forget if I give you all at a go.
Thank you. Okay, so power cables also cause a problem for the magnetically clean environment, but not to the same extent as an electric railway line. So electric railway line induces a very large magnetic field, which is the reason why it causes a problem. What we need to do with the power cables, of course, we need power to manage the site as well and to manage the instruments, but we can shield a power transformer. So for example, we have a generator on site. The generator is well shielded. We're about to install a much bigger generator in another portion of the site to preserve the magnetic field, magnetic clean area. We are installing a Faraday cage around the generator house to restrict and shield the additional noise that comes from the power source. We do find from time to time if there is a problem with the power grid in the area, so fluctuations on the power grid, the noise floor on our magnetic clean environment rises. And then we have to get hold of the local authorities and do something about it to get the problem fixed quite quickly. So although we can live with the power cables, we can't live with the electric railway line system, if I can put it like that. And one of the reasons we can live also with the power system is because the industry in the Hermanus area is low impact industry. It's not high impact industry that requires a lot of 3-phase and higher power generation. So that also helps us a lot. But yes, we are worried about power, and we try to make sure that our facility is shielded against the impacts from power. But the noise floor is not as significant as if we had an electric railway line. Thank you. Hope that helps.
Okay, the next question is, how large an area do all these instruments measure the Earth's magnetic field?
Okay, so I'm not exactly sure what you mean, but I'm assuming you mean how large a portion of the Earth does each of the instruments measure, and this is very dependent on what you're looking for. So we get a very good magnetic survey of Southern Africa by having 2 well-spaced magnetic observatories permanently in Namibia and 2 well-spaced in a different direction in South Africa. That gives us a very good magnetic survey. But then to make sure that we catch the smaller gradients in the Earth's magnetic field, we do what we call geomagnetic surveys at specific survey points throughout the country once a year. So we'll go to the same point every year and take a measurement to make sure that the Earth's magnetic field is not changing adversely in any particular area, and also so that we can check the gradients between the permanent magnetic observatories. So I guess, in short, as scientists, we want to have the instruments as close as possible together so that we get a nice map of what happens across the Earth's magnetic field. But in reality, having two separated by 2,000 kilometers across South Africa with annual points taken is more than enough to keep us, to give us a good map of what's happening over South Africa. We also do a lot of geomagnetic field modeling, where we take the instruments, the measurements that we get, and we actually use the history of what we've got before to create a geomagnetic field model, which allows us to fill in any gaps that we have. And that also helps. Thank you.
Last question from Douglas is the data available for others? The space science is no longer part of the NRF.
Okay, so data access, of course, is always a big question. The short answer is yes, for research purposes, it is available. And it's also available through Intermagnet, which is the international body that we subscribe to. You can also apply to SANSA to utilize the data for research if you can't get it from somewhere else. However, the data is not freely available for commercially developed products and services because it's part of SANSA's data currency. But if you're doing a research project and you would like to use some of our data, then we can definitely make it available to you. Thank you.
Okay, then Judy Stevenson asked, how many space weather forecasters does SANSA need, and does SANSA have currently, and how many would you need by the time the space weather center is fully operational?
Okay, so we did an analysis when we did the audit in 2019, and the number we came up with was 5 that we needed to have in place by 2022. We have one in-house forecaster, and we've just appointed 4 new space weather forecasters who are in training at the moment. It's the first time we've appointed somebody solely as a space weather forecaster, so they're having to undergo training. So our intention is that when we start 24/7 operations, to have 5 in place. How many we need by, say, 2025, that will depend on how the operations goes with the Space Weather Center. But I imagine going up to 8 or 9 by then, because if things go as we planned, because if we're running 24/7, these forecasters will work on shifts. However, at the moment, the calculations have led us to understand that we need at least 5 that are trained and ready to roll on the 1st of April next year.
Okay, thank you. Then Eagle Gladhill asked, could you tell us a little about artificial intelligence and Hermanus? I know that there are neural network enhancements in atmospheric sounding.
Yes, so good question. Of course, one that I can talk about for a long time, because this is what my PhD topic was around all those years ago. So many of our models that we utilize for the space weather forecasting, and also for other work that we do here, is dependent on using empirical data models. And a very good way of developing those empirical data models is to use neural networks. So for many of our, particularly our ionospheric models, as you mentioned, we have used neural networks in the past and still continue to do so today. And we've had very good success in terms of utilizing a neural network to use the data from the past to learn about what we can expect in the future, given certain input parameters. And we also have very large data sets now, which lends itself to neural network works. So we definitely are very much into using alternative modeling techniques in order to ensure the accuracy of our model, and also to utilize the history of what we've learned before from our databases. The solar cycle, which we're dependent on, is nominally 11 years, but actually 22 years because of the reversal of the sun's magnetic field. And this means that actually, if we really want to get good, accurate empirical models of what's going on, we need a 22-year history of data. And for most of our data sets in SANSA, we have that database, so we can utilize those. Thank you.
Thank you, Lee-Anne. I do not see any other questions in the chat room. So maybe just to finalize or to conclude, do you have any concluding remarks?
Are you asking me, Zoma?
Yes.
Just thank you very much for participating and for the interesting questions. And please go and take a look at our virtual tour of the Hermanus facility. It's really a fantastic national asset that we have in South Africa. And if you're ever in Hermanus, please sign up for one of our public tours. If you're part of a research institution or a university, you can also contact us to arrange a special tour for you, your students, your colleagues, so that we can spread the message about the wonderful work that people down here in Hermanus are doing. Thank you.
Okay, thank you, Lee-Anne. Sorry, I see there's a question in the question and answer chat box. It says, hi, happy Space Week to everyone. My question for today is about climate change. Has the South Pole moved closer to South Africa?
Okay, that's a deep question. You can see Tom is laughing because she's wondering how I'm going to answer this. So it's a deep question, and one that we take quite seriously, but we don't have a scientific answer for that yet. The South Pole is moving, of course. The magnetic South Pole is moving, and that's what we measure all the time. We also take a lot of measurements leading us to find out things about the potential reversal of the Earth's magnetic field, which is also very interesting. And these are unanswered science questions that our scientists are busy with at the moment. So we have some geomagnetic experts, and in fact, we've just recently employed a very young, very energetic geomagnetic researcher. And these are the sort of problems that she's battling with right now. Thank you.
One last question from Douglas. He asked if space weather is only affected by the sun interaction with the Earth or others, or are there, I guess, are there other impacts of space weather?
So space weather is driven by what happens on the sun. So the sun is what we call the driver of space weather. So we monitor the sun continuously, and the impact of what happens on the sun on Earth is what we're interested in. But the sun has many impacts, and some of those impacts are not what we call geo-effective. So they're not heading towards Earth. So one of the things we monitor is what is happening on the sun, what is the driver, and is the impact heading towards Earth? So in other words, is the event aimed at Earth? And if it's aimed at Earth, then we have a whole lot of different measurements we take to see what will be the impact when it arrives. We have to do that very quickly, because depending on the driver, it could take up to 8 minutes to get to us, and we have to already have an answer. So that's why we need forecasters on board all the time to be monitoring the sun and delivering that. I have a feeling your question might also be aimed at, is there space weather on other planets? And the question is yes, there is. SANSA is not currently studying that, but I do know of a number of interplanetary scientists who are interested in space weather on other planets, particularly, for example, Mars, because there's a lot of interest in the Mars mission at the moment and what it would mean for people to reside on Mars. But in terms of Earth, we monitor the sun all the time. We look at the sun's drivers, and then we look at whether or not what is coming off the sun as a result of those drivers is geo-effective. In other words, is it heading for Earth? Is it going to impact us? And if it is, we move very quickly to calculate what that impact can be. Thank you.
Thank you, Lee-Anne. In the interest of time, I will then close all the questions and thank everybody for attending our first webinar. Tomorrow, we'll have another webinar where we will be meeting the space weather forecasters. So please join us again tomorrow at 2 o'clock, and we'll be talking to 4 of the SANSA's space weather forecasters. Thank you, everybody, and have a lovely afternoon.
Thank you.